Welcome back, students. In this video, I want to talk a little bit more about the position of equilibrium and how to decide which side your equilibrium is going to lie to in an acid-base reaction. We've already talked a little bit about position of equilibrium in earlier videos, but now that we've gone through the qualitative process of trying to figure out which acid is stronger, I want to revisit the topic. If I have a reaction like the one I'm showing here, I want you to be able to figure out, without using pKa's, what side the equilibrium is going to lie to. One of the things that you have to remember is that the side of the weaker acid and weaker base is the side the equilibrium will lie to, because strong acids and bases always react to form the more stable and also weaker acids and bases. So instead of using pKa, we're going to look at the qualitative version here and look at just the structure. One thing that you need to do to start with this is to figure out what in my structure or what in my reaction are my acids and bases. So first, let's identify this as an acid and this is a base. Then we can draw the conjugate acid-base pairs, where if this is my acid, then over here is my conjugate base. And if this is my base, then over here is my conjugate acid. And because we just spent a bunch of time looking at the stability of conjugate bases, I want to pull out the bases from this, keeping in mind that the first one isn't technically labeled conjugate, and that's perfectly fine. What we're trying to do is pull out the bases. So this one versus this one. And we want to decide which one of these bases is going to be the more stable one, because the more stable the base, the weaker the base. We go through that ARIO, the ARIO process. We figure out where the extra electron density is. So here, the extra electron density is on a carbon. Over on the left, the extra electron density is on an oxygen. We look at the periodic table, we say carbon and oxygen are in the same row, so we consider electronegativity. Oxygen is more electronegative than carbon, which makes oxygen better able to stabilize the extra electron density. This then is the more stable of the two bases. Remember that the more stable the base, the weaker the base. And your overall key here is that your equilibrium will always lie to the side of the weaker acid and the weaker base. Now, do you have to go through and also figure out which one's the weaker acid? No, because if you figure out which one is the weaker base, your weaker acid is always paired with that. So you don't have to do all that extra work. Therefore, for this particular reaction, your equilibrium is going to lie more heavily to the reactant side. So I'm just going to make this arrow bigger here to show that we have the reactants are going to be in the greater proportion because the reactants are our weaker acid and our weaker base. Basically, what we're doing is we're taking the idea of position of equilibrium that we talked about when we learned about pKa, and we're going to fold in that ARIO method. Now I want you to give some a try. I don't want you to look up pKa's. I want you to look at the structures and use the ARIO method to decide which side the equilibrium will lie toward. Go ahead and pause me, give yourself a moment to figure these out, and then we can reconvene. All right, let's reconvene. In this first one, what I did to figure out that the equilibrium is going to lie more heavily to the right was I found my bases. Here is a base and here is a base. I looked at the bases and I started by considering atom. My extra electron density is on oxygen in both instances, so that doesn't do me any good. Next, I go to resonance. The base with the pi bond here, that can participate in resonance, whereas OH hydroxide, it cannot. Because the base with the pi bond can participate in resonance, that makes this one more stable. And remember that stable bases are weak bases. And because your equilibrium always lies to the side of the weaker acid and the weaker base, the equilibrium is going to lie to the right in this example. Let's look at the next one. In the next one, we're still seeing the equilibrium lie to the right. I'm going to do the same process. I'm going to find my bases. So here's one, and here's my other one. My extra electron density is on carbon and nitrogen. In this case, we're looking at atom because the atom changes as to where the extra electron density is sitting. Carbon and nitrogen are in the same row, and because they are in the same row, we consider electronegativity. Nitrogen is more electronegative than carbon, and it is better able to stabilize extra electron density, which makes the amide ion, the NH2, more stable. And because it's more stable, it is a weaker base. And weaker bases are the side that your equilibrium will lie to. So again, we're lying to the product side in this reaction. In this example, we're going to do that other notation where you're going to look at this and you're going to decide, does the equilibrium lie to the left or the right? So give yourself a moment, pause me, look these through. Again, I want you to use ARIO and not pKa's to logic your way through which side the equilibrium is going to lie. Now that you're ready to look at these, let's compare answers. For the first one, I'm going through the same process again where I'm finding my bases. So here is a base and here is a base. The base that is going to be more stable is the one that is going to participate in induction because my extra electron density is on the same atom and both of these can participate in resonance. So those two criteria don't do me any good. So the next thing I do is I look at induction and I see a chlorine over here that's going to pull electron density toward itself, making the base on the left more stable. And because that one is more stable, it is weaker. Remember that the equilibrium always lies to the side of the weaker acid and the weaker base. So in this first example, the equilibrium is going to lie to the left. Let's look at the next one. And the next one, I'm again going to go through the same process. I find my base, I find my base. When I consider these two bases, the atom where the electron density sits does not change. It's on carbon in both of them. Neither of them participate in resonance. That's why we needed to really make sure we could draw resonance arrows. So don't draw any fake resonance arrows that are false. Neither participate in induction, so all that's left is orbital. The lone pair here is in an sp hybrid orbital. The lone pair here is in an sp2 hybrid orbital. The sp hybrid orbitals hold the electron pair closer to the carbon nucleus, making less, distance between the positive and the negative, which stabilizes that extra pair of electrons. And because the sp hybrid orbital is stabilizing that pair of electrons, stabilizing means more stable, which means this is the weaker base. And because that one is the weaker base, again, in this example, the equilibrium will still lie to the left. Let's wrap up. In this video, we looked at ARIO and how you can use it to figure out the position of equilibrium. And we did some more practice to figure those things out. I really want to make sure that you are capable of figuring out what side the equilibrium lies toward, utilizing just the structure of that compound and not relying super heavily on pKa's. You need to be able to state if an equilibrium lies to the left or the right, and you also need to be able to determine if the equilibrium lies to the left or the right, and then communicate that with the proper equilibrium arrows. As always, thanks for your attention. This is Katoni signing out.